Hello and welcome back to another video in the Introduction to Windows Forensics series. This time we're going to take a look at a new version of Plaso called Heimdall and Log2Timeline. But first, let's not get ahead of ourselves. While there's a chance you're already familiar with super timeline creation tools, there's also a chance that you've never heard of Plaso or Log2Timeline. So let's define some terms. You can see that I have the GitHub page for this particular project shown on screen, and at the top of the page you'll find that Plaso is defined as the Python-based backend engine used by Log2Timeline, whereas Log2Timeline is the tool itself that we'll use to extract timestamps from various files on a computer. What we're actually doing is extracting data from a large number of forensic artifacts, aggregating that data, placing it in temporal order, and writing it to a spreadsheet. When we do this, we create something called a super timeline, which is an all-encompassing, very large aggregation of data that shows a complete picture of all of the forensic artifacts that we're able to obtain off of a computer system. So obviously with that, we need to understand how to parse that data because it's so much data that what we're looking for may get lost in the mix. So we have to become really good at knowing where to find what we're looking for and how to use a tool like Excel to actually sift through that data and parse it. Now it's important to note that most of the data we're talking about here are disk-based forensic artifacts, things like prefetch, user assist, and other registry-based forensic artifacts, MACB timestamps for files, cache cookies and history from browsers, and things of this nature. In fact, a lot of the things we've covered in previous videos in this series. But we can also extract timestamp artifacts from memory using plugins with volatility, for example, and we can include that data in the creation of a super timeline as well. Now I've got a page pulled up here from the SANS Digital Forensics and Incident Response blog that actually provides a template that we can use with Log2Timeline that will colorize and organize the output of this particular tool and make it much easier for us to parse the data. In fact, you'll find completed instructions of how to do that on this page, and I'll include a link to this in the video's description. This particular image is a blown up screenshot of what a small section of a super timeline will look like. And of course you can see date and timestamps and time zone information. You can also see source types indicating from where a particular artifact was obtained. Things like prefetch, deleted registry keys, flash cookies, user assist keys, etc. So again, this is just a very small excerpt of what a super timeline looks like, but it gives you an idea of the kind of output we can get from running this tool. Now, as I mentioned, the current version as of the creation of this video is called Plaso Heimdall, and it carries a version number of 2017-0930. The previous version was 1.5.1, so you can see that they've shifted in this release to a date-based version format. We're also told in this blog post that we can expect more frequent updates to the tool. Now, there have been a lot of back-end improvements and changes. There's also been some new features added to the tool, including a parser for AM cache, which you can see here. I'm particularly interested in this. By the way, if you're not familiar with AM cache, you should check out the Windows Application Compatibility Forensics video, which I'll link to in the top right of your screen now. We'll also see that there's a new Plaso front-end tool called psteel that can help us more easily process an image and produce human-readable outputs. So we'll take a look at that as well. So in the next section of this video, we're going to switch over to a Linux box and run Log2Timeline against a Windows 10 forensic image that I've acquired. We'll produce that timeline and use the template that SANS provides and look through the vast amount of data that we're able to obtain, and then talk about how we could sift through that data to actually find the needle in the stack of needles that we're looking for. So let's switch over to the next section of the video. In this section of the video, I'm using a stock Ubuntu 16.04 installation running in a VMware Fusion virtual machine. You can see that I've given this VM 2 gigs of RAM and about 20 gigs of disk. I've installed the base OS and the updates, but I've done no further customizations other than changing the wallpaper, as you can see here. So the next thing I did was, I went over to the GitHub page for Log2Timeline/Plaso, and as stated here, I installed the PPA, or Personal Package Archive, for the project. I then ran apt-get update to make the changes take effect, and then apt-get install python-plaso and Plaso-Tools, which will install everything we need to get up and running. Now, as you might imagine, there is no front end for Plaso because Plaso is, of course, the engine that powers Log2Timeline, so there is no Plaso command. There is, however, a log2timeline.py command, which is the main command we'll use to invoke the software, and if we use that with a -V, we can see the version that we have installed, which is 2017-0930, or Heimdall. Now, as luck would have it, while I was filming this section of the video, and after I had filmed the previous section that you just watched, the Plaso team released 2017-1118, which, as you can see from the very brief release notes here, is a very minor update that fixes a couple of small issues and adds a parser for Sophos antivirus SAV logs. So if I ran updates right now, and then ran log2timeline.py-V again, we would actually be on that version. The Plaso team did indicate they were going to be focusing on more frequent, smaller releases, so clearly they've already begun that process. This still doesn't change the fact, however, that Heimdall is the major release, and that's still what we're going to be concentrating on in this video. So in the next section, we'll take a look at the basic usage of the tool. Okay, first up, let's talk about psteel. As I mentioned in the first section of this video, psteel is new as of Plaso Heimdall, and according to the documentation, it is now the quickest way to generate a timeline with Plaso. In fact, if you look at the actual source code on GitHub, you'll notice that it states that psteel combines the log2timeline and psort tools into a single tool. It currently does not support any of those two tools' flags because it has its own set of flags, but it's extremely easy to use. As you can see from the documentation, they've specified 3 arguments here. --source to specify the actual disk image or mount point, -O to specify one of several different output formats, and -W to specify the file that will be written as output. So first off, you'll notice that I am currently located in the mount point of an external hard drive that I've got connected to this VM. You'll notice a rather large petya.dd image file in the root of the drive, and as the name implies, this was taken from a computer infected with the Petya ransomware that came out a little while back. This is what we're going to be using for our lab image. So without doing anything else, let's go ahead and run psteel.py with no arguments, and we'll notice that it gives us a usage prompt, and we do see there are quite a few other options besides the --source, -O, and -W flags that were used in the documentation. However, for our use case, we'll stick with those basic options. So let's use --source and actually specify petya.dd, -O, and instead of specifying L2T CSV, I'm going to type list so that the software will return a list of my available options for output, and then -W will be output.csv. Now when I run this, it actually isn't going to do anything but show me the different output formats, and as you can see here, L2T CSV is the top option, but it's actually listed as the legacy log2timeline format. So we're not going to be using it, but right underneath that you'll notice XLSX, which of course is the Excel spreadsheet output format, and that we will be using. And underneath that you'll notice several other options available to us as well. So let's go ahead and change this to XLSX, and then we'll go ahead and change the output file extension to XLSX as well, and that command is all we need to get started. However, I'm not actually going to run it. The reason why is because I want you to know that you do not have to specify a disk image as the source. Rather, as I mentioned, you can specify the mount point for a disk. For example, I could mount this petya.dd image and then give it the mount point as the source. Or perhaps I've got an external hard drive connected to a write blocker, and I wanted to analyze it instead. Now, typically, I do use a disk image file, as in this example, with psteel or log2timeline, but every once in a while there may be a need to do something different, as in specifying a mount point. Plus, it's good practice to understand how to mount a DD NTFS image in Linux. So let's go ahead and create a mount point placeholder here under temp. We'll just call it lab image. And now let's run the mount command. We'll use -O to specify some options. And the first thing we'll specify is RO for read-only. We'll specify loop because this isn't a physical device, rather it's an image file. We'll use show_sys_files so that the otherwise hidden NTFS metadata files will be shown. And then we'll use streams_interface equals Windows so that any alternate data streams that may be present will be visible. We'll use -T to specify the type of mount, which is NTFS. We're going to be mounting petya.dd, and again the destination will be /temp/labimage. And you'll notice we're returned to the prompt with no errors. So let's look at /temp/labimage, and you'll see that does indeed look like the root of an NTFS volume. So it looks like it did mount successfully. So now if we go back up to our pstill command and change the source to /temp/labimage, we'll change this back to XLSX and change this to XLSX. And now this is the alternate command, which I will run. And as you can see, it says processing started, and we are now off to the races. Okay, we are now looking at the output from the pstill command that we just ran. It ended up taking about 1.5 hours to finish processing, but of course that time can vary greatly depending on the size of the disk image or mount point, whether or not the data is being analyzed from a mechanical hard drive or a solid state drive, and various other factors. Now you're looking at the default view. I haven't modified anything, and you can see that by default the column headers are in bold, filtering has been enabled, and if we scroll, the top row has been frozen to make it much easier to review the data. So these are some welcomed defaults. Let's now take a look at each of these columns and the associated data therein. The leftmost column is called date time, and of course that's fairly self-explanatory. This is one of the most important columns and provides timestamp related information pertaining to any given artifact. Now you'll notice a lot of January 1st, 1970 timestamps here, but that's simply because timestamp related information was unavailable for this particular artifact. If we scroll down, we'll start seeing legitimate and meaningful timestamps. The next column is called timestamp description and provides some context with regards to the type of timestamp. For example, is it content modification time, creation time, file last modification time, and these other options that you see here. Source will specify the type of forensic artifact. For example, we've got AM cache, which is new in Plaso Heimdall, Windows event file related information, link file information, registry and web history information. Source long will provide additional types of sources, including some more verbose descriptions. We'll again see AM cache, app compact cache, Chrome cookies, Firefox cookies in history, Google Analytics cookies, Windows shortcut data, Windows event log data, and various other options. The message column will vary greatly depending on the type of artifact, but this provides additional information pertaining to any given artifact. For example, we'll see registry paths, file paths, and link file related information, and various other data. So obviously a very important column as well. The parser column will show the type of parser used to parse that particular artifact. The display name column will actually show the path to the artifact on disk. So in this case, we'll see a lot of registry paths for the system hive. And then lastly, the tag column is not populated by default. So again, let me just quickly scroll through this massive amount of data. You can see from the scroll bar on the right side just how much data was collected. But we see everything from timestamp related information for files, we see link file information, web history information, link file information, and just a huge amount of forensic data. So all of these forensic artifacts have been parsed and put in temporal order into this giant timeline, or super timeline as we call it. So obviously you can see that this would be of very great value to a forensic investigation. Now, of course, because there is so much data, we very well may want to filter to only show the data that we're interested in. So I've got another spreadsheet here called output_filtered, where I've filtered on a source of web hist, as you can see from this column. Looking at the source long column, you'll see things like Google Analytics cookies, Firefox history, Firefox cookies, Chrome cookies, and things of this nature. The message column will show, of course, some additional context, including bookmark URLs. We'll see cookies for Puriform, Yahoo, Google, and various other information pertaining to these web-related artifacts. As we continue to scroll, we'll see, of course, the parser column, which again contains the parser used to parse this particular artifact. And of course, we see the display name column showing the source on disk from which this particular data was obtained. For example, we see a lot of references to places.sqlite, which of course is one of the main forensic sources of data in Firefox. And then lastly, the tag column, which again is not populated by default. So this just shows how easy it is to filter to only show the data that you're looking for, because again, there is so much data, you need to have some context. Of course, another thing might be to define the dates of your particular investigation and filter the timeline to only show that time period, which can drastically reduce the amount of artifacts that you see on screen. So next, I do want to mention that while we did use the pstill front end, you don't have to do that. You can still use log2Timeline and psort manually. In its simplest use case, log2Timeline can simply have an output and an input argument. So this is called the kitchen sink approach. And in this example, we've got the output of test.plaso and then the input of this test.vhd image file. It's a little counterintuitive because you think it would be input-output, but again, it's output-input. And looking at this documentation on the official GitHub page, there are numerous other options, of course, with log2Timeline, where we can filter just on specific data instead of using the kitchen sink approach, and again, numerous other options. Now, the psort tool will then take that Plaso file that was generated with log2Timeline and enable us to apply time zone related information, as you see here, or to provide various other modifications and massaging of that particular data. We can filter things, we can take slices of time that we're interested in. So again, psort is a very useful tool to further process that data. So these are obviously still available, and again, you don't have to use the pstill front end, but pstill certainly does make it very easy to quickly generate a timeline and get up and running with minimal effort. The last thing I want to mention is in the first section of the video, I had shown the free template from Sans that colorized some of this timeline output. If you intend to use that, you'll need to use the L2T CSV format instead of the XLSX format, because the template actually requires you to import a CSV file into that particular template. So again, you'll want to use the legacy L2T CSV format and not the XLSX format if you decide to use that colorized template. So that pretty much wraps up this video, and I think I've covered everything I wanted to cover in terms of the basic usage of Plaso and log2Timeline, and hopefully you can see just how valuable this data can be to an investigation. Basically, you've got a one-stop shop to parse a large number of forensic artifacts and put them into this large spreadsheet that you can then filter and build a timeline of all of the events pertaining to your case. So if you have any further interest in additional Plaso log2Timeline videos that may cover more in-depth topics, please do let me know in the comments. As always, I would greatly appreciate it if you would subscribe to the channel if you haven't already. That would help me out. Please also like and share these videos. That would also be greatly appreciated. But otherwise, I would like to thank you for taking the time out of your day to watch this video. I hope it's been useful and informative, and I'll see you in the next video.